Welcome to my channel. Have you ever wondered how a tiny drop of insecticide can attack the nervous system of animals like a secret weapon? How it affects the non-target species? This hidden mechanism is what makes insecticides deadly to pests as well as other living organisms on the planet. Watch this video to get answers to the questions like what are organochlorine, how they cause damage to living organisms. This video is going to be very interesting and helpful for you, as you are receiving a series of videos related to toxicology, so it is more important for you to subscribe this channel to get new videos on time. So, press the bell icon below this video. Also comment and like and share this video with your fellows. After watching this video, you will able to understand what are the mechanism of action of pesticides including organochlorine, organophosphate, carbamates and pyrethroids. Let's see how these organic chemicals affects living organisms. Before going towards main topic, mechanism of action of organochlorine, one should know that what chlorinated hydrocarbons are. Chlorinated hydrocarbons are chemicals made up of the elements carbon and hydrogen at the combine for the hydrocarbon part of the molecule and chlorine atom substituted for hydrogen where a hydrogen atom was normally bonded to a carbon atom. Chlorinated hydrocarbon insecticides are highly lipid-soluble and are readily absorbed through the skin, therefore rapidly distributed to liver, kidney, and brain, and accumulate and persist in adipose tissues, with the result that the half-life in a body is typically protracted and may be measured in months or even years. The chlorinated hydrocarbons are stimulants of the nervous system. Their mode of action is similar in insects and humans. They affect nerve fibers along the entire length by disturbing the transmission of the nerve impulse. More specifically, the members of this group of insecticides disrupt the sodium-potassium balance that surrounds the nerve fibers. The result of this imbalance is a nerve that sends transmissions continuously rather than in response to stimuli. Let's see how action potential normally generated and travel along the neurons. In response to signal, the soma end of the axon becomes depolarized. The depolarization spread down the axon. Meanwhile, the first part of the membrane repolarizes. Because sodium channels are inactivated and additional potassium channels were opened, the membrane cannot depolarize again. The action potential continues to travel down the axon, the direction of travel shown in the figure, and the previous part of membrane come to resting phase. Normally during action potential generation, depolarization is followed by repolarization and hyperpolarization. However, insecticides interact with the neuronal membrane by altering the membrane permeability for potassium, sodium and the calcium-mediated processes. By inhibiting these functions, the repolarization of the nerve is disturbed, resulting in hyperexcitability of nerve fibers. Despite the similarity of many of the compounds within each of the three subgroups, the individual toxicities vary greatly. The compounds also vary greatly in their ability to be stored in tissue. For example, methoxyclar, a colorless, crystalline organic halogen compound used as an insecticide. Its structure is very similar to DDT, but its toxicity is far lower. It acts more rapidly, is less persistent, and does not accumulate in the fatty tissues of animals as does DDT. Storage in fatty tissue is actually a strategy that the body uses to remove toxic materials from active circulation. Fatty storage prevents the toxic agent from reaching in the circulation and consequently on various organs like liver, kidney, etc. DDT-type insecticides interact with the neuronal membrane by altering the membrane permeability for potassium and sodium and the calcium-mediated processes. By inhibiting these functions, the repolarization of the nerve is distributed, resulting in hyperexcitability. Do you know what are neurotransmitters? And cyclodines and cyclohexane antagonize neurotransmitters? Come to know that neurotransmitters are endogenous chemicals that enable neurotransmission. They are a type of chemical messenger which transmits signals across a chemical synapse from one neuron, nerve cell, to another, target, neuron, muscle cell, or gland cell. While gamma-aminobutyric acid is a naturally occurring amino acid that works as a neurotransmitter in brain, it is considered an inhibitory neurotransmitter because it blocks or inhibits certain brain signals and decreases activity in nervous system. Cyclodines and cyclohexane compounds stimulate central nervous system. These compounds antagonize the neurotransmitter, gamma-aminobutyric acid, permitting only partial repolarization of the neuron and thus uncoordinated nervous excitation. Owing to their lipophilicity, organochlorine compounds are partitioned and stored largely in adipose tissue, where they are biologically inactive. There is an equilibrium between body fat and free circulating compounds. Redistribution and mobilization of fat, for example, due to disease, aging or fasting may result in mobilization of stored organochlorines in quantities that may lead to manifest toxicity. Owing to the different patterns of use of organochlorine insecticides in industrialized and developing countries, the pattern of distribution of the residues in human fat, including breast milk, differs between countries. Now summarize the mechanism of action of organochlorine insecticides. Chlorinated hydrocarbons act as diffused central nervous system stimulants. They do not act upon any specific receptors. Their possible mechanism of action may be: they change the electrical activity in the central nervous system by altering sodium and potassium flux across the nerve cell membranes. They increase the concentration of free ammonia and glutamine in the brain. They inhibit activity of sodium, potassium and magnesium ATPase in the nerve endings of central nervous system. Cyclodines inhibit GABA receptor-mediated chlorine transport and clamidulin-regulated calcium pump activity in the brain. Let's learn mechanism of toxic action of organophosphate insecticides. These are less persistent than the organochlorine insecticides, a property due to which they are preferred to the organochlorine insecticides. In principle, organophosphate compounds react with the active site of acetylcholinesterase, a serine hydroxyl group. Cholinesterase is a family of esterases, enzymes that lyses choline-based esters. In other words, all organophosphate compounds are anticholinesterase agents, i.e., they inhibit the enzyme cholinesterase at the neuromuscular junction. During normal muscle contraction, the cholinergic nerve fibers of autonomic system liberate acetylcholine at the neuromuscular junction. The acetylcholine excites muscle fibers and, consequently, muscle contraction takes place. Very soon acetylcholine is splitted by cholinesterase present at the neuromuscular junction into choline and acetyl coenzyme A. This picture explains the phenomena nerve transmission. Acetylcholine is a chemical neurotransmitter found widely in the body. It triggers the stimulation of postsynaptic nerves, muscles, and exocrine glands. While acetylcholinesterase is an enzyme that rapidly breaks down the neurotransmitter, acetylcholine, so that it does not overstimulate postsynaptic nerves, muscles, and exocrine glands. Acetylcholinesterase inhibitor is a chemical that binds to the enzyme, cholinesterase, and prevents it from breaking down the neurotransmitter, acetylcholine. With toxic doses, the result is that excessive levels of the acetylcholine build up in the synapses and neuromuscular junctions and glands. Organophosphate insecticides are structurally similar to acetylcholine and act as acetylcholinesterase inhibitor. At neuromuscular junction, acetylcholine is released as a result of stimulus to transmit the massage. The organophosphate competes with acetylcholine and binds with cholinesterase, thus inhibiting normal function of cholinesterase enzyme. As a result, these inhibitors block the breakdown of acetylcholine into acetyl coenzyme A and choline. This figure shows the splitting of acetylcholine into choline and acetyl coenzyme A by the action of acetylcholine esterase enzyme. Actually, splitting of acetylcholine by acetylcholine esterase prevents its accumulation at the neuromuscular junction and thus assists in muscle relaxation after each contraction. In its usual course of action, the choline esterase first gets acylated by losing one hydrogen and then fastly recovers by using one molecule of metabolic water. Actually, the organophosphate compounds are structurally similar to acetylcholine. At the enzyme site, they compete with acetylcholine and bind with cholinesterase, thus inhibiting its normal function. The organophosphate compounds phosphorylate the cholinesterase and form a stable complex. Ultimately, the enzyme fails to recover quickly. Actually, splitting of acetylcholine by cholinesterase prevents its accumulation at the neuromuscular junction and thus assists in muscle relaxation after each contraction. These events bring about an accumulation and consequently increase of acetylcholine esterase at the neuromuscular junction, which in turn, respectively, excites the muscle fibers and produces repetitive muscle contraction that causes tremors in the body muscles of insect, and the insect finally dies of exhaustion. Let's study mechanism of toxic action of carbamates. The primary way that insecticidal carbamates work on both target and non-target species is through the inhibition of the enzyme acetylcholinesterase. Acetylcholine is a substance that transmits nerve impulse from a nerve cell to a specific receptor such as another nerve cell or a muscle cell. Acetylcholine, in essence, acts as a chemical switch. When it is present, produced by the nerve cell, it turns the nerve impulse on. When it is absent, the nerve impulse is discontinued. The transmission ends when the enzyme acetylcholinesterase breaks down the acetylcholine into choline and acetic acid. Without the action of this enzyme, acetylcholine builds up at the junction of the nerve cell and the receptor site, and the nerve impulse continues. Carbamate insecticides block, or inhibit, the ability of this enzyme, acetylcholinesterase, to break down the acetylcholine and end the nerve impulse. Carbamate inhibition of acetylcholinesterase is a reversible process. Estimate of the recovery time in humans range from immediate up to 4 days, depending on the dose, the specific pesticide, and the method of exposure. The breakdown of carbamate compounds within an organism is a complex process and is dependent on the specific pesticide structure. In a nutshell, the mode of action of carbamates, like organophosphate, is the inhibition of acetylcholinesterase. Carbamates are potent reversible inhibitors of cholinesterase. In addition, all the carbamates inhibit alioesterase of insects, but they kill insects and mammals entirely by cholinesterase inhibition. The mechanism of inhibition of acetylcholinesterase and its reactivation is shown in this figure, taking an example of carbaryl, a widely used carbamate. Let's study mechanism of toxic action of pyrethroids. There are 2 types of pyrethroids. The type 1 esters affect the sodium channels in nerve membranes with prolongation of sodium influx causing repetitive neuronal discharge and prolonged after potential but no severe membrane depolarization. The type 2 alpha-cyanoesters lead to greater and more prolonged sodium influx with persistent membrane depolarization and eventually nerve blockade. Whereas the first group exerts its main effects on synaptic transmission causing hyperexcitability and tremor, the second group shows its first effects on the sensory nervous system. Other actions include inhibition of sodium-magnesium ATPase, adenosine triphosphatase, and alteration of calcium and chloride ion homeostasis. Hopefully this video will be beneficial for you. Thanks for watching. Like and share this video. Subscribe this channel to get more informative videos and to become part of a growing scientific community.